Okay, so we're going to move to Chapter 3, and Chapter 3 will just add some new nuances to this thing called linear programming. So at this point, we understand decide, decision variables, our objective function, our constraints, and we're getting pretty good at picking those things out using Excel to model them. We understand what sensitivity report is all about. There are some things that we need to keep in mind when we set these up. And a couple concepts is, we may work with these for years and years, and we may work with, we may share these with other people as we, in a job situation. So familiarity, simplicity, clarity are all important. So I'm going to show you a technique. It's called summation variables, and I'm going to show you a couple ways to handle this situation. And I'll tell you what. Hopefully you hung on to Mary's pie, so we'll use that as an example. We'll use that to make up an example. Okay. So here's when summation variables are used. A lot of times I have constraints that are based on the whole, okay? Based on the final solution, which is unknown at this point. Let's say I don't know what total production is, but I know I want less than 30% of total production to be in terms of widget 1. I want no more than 50% of total production to be in widget 2. But I don't know what that total production value is at this point. So anytime we're dealing with totals or wholes, we need to set up a variable for it, okay? So the use of summation variables, representing the sum or all or part of a decision variable, with summation constraints may simplify a model's formulation. Okay, so let's take a look at an example. We're making 3 television models. Each model uses 2, 3, and 4 pounds of plastic, respectively. We have 7,000 pounds of plastic available. No model, and this is given to us by the marketing people, no model should exceed 40% of the total quantity produced. The problem is, I haven't decided what the total quantity produced is. If I knew it was 1,000, I could say, hey, everything that has to be produced less than 400, right? I could hard code 400. But I don't know what the total quantity produced is. So it also gives me the profit percentage, 23, 34, and $45 respectively. All right? So here's what this might look like. Okay? Max, the objective function, you guys can figure that out. Maximize 23x1, 34x2, 45x3. There's my plastic, subject to 2x1 plus 3x2 plus 4x3 is less than 7,000. The thing that's new to us was that, hey, each TV should account for less than 40% of total production. But we don't know what that is. So here's what we could do. We know total production is what? X1 plus X2 plus X3, right? So we could do this. We could say X1 is less than or equal to 40% X1 plus X2 plus X3. But remember what that looks like. We said we always want on the right-hand side, what do we always want on the right-hand side? We don't want variables over there. We always want what? A coefficient over there. So mathematically, follow me through with this. If we took this first one and we put it in Excel Solver, this is what it looked like. Okay, we have X1 is less than or equal to 0.4 X1 plus X2 plus X3. So let's go a little bit further. X1 is less than or equal to, so we multiply that through 0.4 X1 plus 0.4 X2 plus 0.4 X3. I want to get the variables off of that side. So if I do, how do I get the variables off that side and onto the other side? What do I have to do? Algebraically? I have to subtract it from both sides, yes? So if I subtract minus 0.4 x1, 0.4 x2, 0.4 x3, it becomes 0 over here. So I have to do the same thing on this side. 0.4 x1 minus 0.4 x2 minus 0.4 x3. That's 1 x1 minus 0.4 x1. That gives me 0.6 x1 minus 0.4 x2 minus 0.4 x3 is greater than or equal to 0. So if I put this into Excel solver, I would use the coefficients 0.6, negative 0.4, negative 0.4, has to be greater than or equal to 0. And it works. Okay? Did I do the math right? You guys are looking at me strange. Did I do the math right? Okay? It works. However, it's not intuitive to me. But that is saying less than 40% has to be in X1. It's not intuitive. I don't see it that way. Do you see it that way? Probably don't think that. What we can use is a summation variable. Okay? And what a summation variable is, it's a variable that represents the whole. So instead of doing it this way, what I would do is I'd create a brand new variable that represents the whole. Now, to define that, we actually define something called a definition constraint that makes the new variable for me. X4, we're going to say, is total production. So X1 plus X2 plus X3 equals X4. Or X1 plus X2 plus X3 minus X4 is equal to 0. This itself is called the definition constraint. It defines X4. If we tell solver to adhere to this constraint, X1 plus X2 plus X3 minus X4 is equal to 0, it'll force X4 to be the sum of those other three, right? So now X4 is my total value. I can use X4 now for everything else. X1 has to be less than or equal to 0.4 of my total, which is X4. Or that. That is how I'd want to write it in Excel solver. Okay? 1 for the coefficient here, 0.4, negative 0.4 for the coefficient here. That is saying less than 40% of the total production can be in X1 TVs, X1 brand TVs. Now this is used a great deal in any kind of model that deals with mixtures. Okay, marketing mixtures. You know, you can only have so much in product A, so much in product B, so much in product C. I think I mentioned we haven't done a lot of these, but like portfolio models. You know, you might tell your broker, I want less than 20% of my investment to be in international funds, and no more than 30% to be in hedge funds, right? But you're maybe not sure what the investment is at any given point, okay, when you're formulating this model. So this is when we would use summation variables. Okay? So let's go through an example. I think that's the best way to make sense of this. Let's go to Mary's, and I'm going to take it back to the original. I'm going to remove the forcing us to make chocolate pies. I'm going to remove chocolate pies altogether. Let's take it back to the original. Okay. Let's say for whatever reason, Mary's is known for her custard pies, and she has a hard constraint that at least 50% of any production she puts out has to be in custard pies. At least 50% has to be in custard pies. The current model, that's not the case, right? It's not the case, not 50%. But let's say they're telling us, or she's telling us that at least 50% has to be in custard pies. Here's what I would do. Okay, I would come up here and I would define a new variable, and I'm going to call it T for total. Okay, my T for total. What would the definition of that look like? How would I define T? What would the definition constraint for T be? I would need to add it into this section. what would that look like? What is t? The total, which is represented with what? Well, we don't need the greater than yet. We just need to define this thing. We need a definition of this thing. How do we define it? What's that? Yeah, really, we would add a constraint in here. C plus F is equal to T, or C plus F minus T is equal to 0. That is the definition constraint. That creates T. Okay, that creates the variable T for me, which is the total. Now I can write the constraint based on T. Now I would say custard pies has to be greater than or equal to 50% of T, or another way to write that is custard minus 0.5 T is greater than or equal to 0. Okay? That will do it for me. Okay, that will do it for me. I need to add those two in to my constraints. And let me show you how we do that on Excel. Okay, let me show you how we do that on Excel in a second. So this is a constraint called the definition constraint. It defines it, it creates it, it builds it, it brings it to life. It brings T, the total, to life. Then I can use it. I can use it a lot of different ways. Okay, but in this case, I'm using it to define the custard pie production has to be greater than or equal to 50% of the total. So let's go up here and let's do it. In this case, I'm going to insert, I'm going to click on F and do an insert, and I'm going to create it over here in this E column, and I'm going to put a total here. Okay? And I don't want to put a sum in there. I don't want to put C2 plus D2. It's a decision variable, just like custard and fruit pies. Okay? It's just treated like another decision variable. It has a coefficient of 0 because I'm not making profit off the total. I'm making profit off of custard and fruit pies. I'm going to need to change my formula here to include it. I'm going to have to say sum product C2 through E2 because I want to include this. C4 through E4. And I'm going to copy that down as well, so it adjusts everything appropriately. Okay. Now I haven't added in my two new constraints yet, but let's do that right now. I'm going to add in the definition constraint. So I'm going to go down here and put in def, okay, for definition. C plus F minus T is equal to 0. What's the coefficient here? You can't see it, but it's an implied 1. The coefficient here is an implied 1. The coefficient here is an implied, well, not implied, but it's -1. And that has to equal 0. Okay, let's put in this one. And this is, let's just say mix. And let's say marketing. Mix. The coefficient for custard pies here is 1. Custard, there's no fruit pies in this equation, so we're just going to put a 0. This is -0.5. Copy that down. Has to be greater than or equal to 0. So the only thing that's new in here, okay, think about, I know some of you guys are catching up, so I'll talk through this. What we added was a new decision variable. It is a summation variable. Okay, it's called the total summation variable. It's treated just like any other decision variable. It's going to be in the changing cells. For most of these, it has a 0 coefficient. Or I can leave it blank, or I can put a 0 there. It's your preference. But it has a 0 coefficient. Down here is what's building it, because I'm forcing it to be equal to the total of these two things via this constraint, which I need to tell solver about in a second. Once I've defined it, I can use it. C has to be greater than or equal to 50% of T. So let's go to solver. Okay, my objective function is maximize F4, good. By changing cells C2 through D2, well, I really want to change all three of these. Okay, I want to give Excel prerogative to change all three, because this constraint down here is going to force it, E2, to be the sum of those two. Let's see, F6 through F9 is less than or equal to H6 through H9. That's okay. Now let's tell it about my two new constraints. Add F10, and then we haven't used this relational operator yet, but notice there's an equal sign, is equal to 0, which is H10, click add, and F11 is greater than or equal to H11. Okay, so I stuck with the model. You know, I stuck with everything's in the same column. We're talking about F's and H's. The row 10 constraint defines it, creates it. The row 11 constraint uses it. Let's try it. Let's resolve now. Click solve. Solver found a solution. All constraints and optimality conditions are satisfied. Click OK. And notice now it's making exactly half custard pies and exactly half in fruit pies, because we told it had to make exactly half in custard pies, right? We told it at least 50% of production had to be custard pies. So what is this then? What is this? I know it's self-imposed, but because this is solved with equality, what kind of constraint is that? It's binding. We're the ones that imposed it, but what does that tell me? If this is binding, if I relax that constraint, Ken, if I said it only had to be 45%, properly grind, right? Okay, and we could see that how? We could look at the sensitivity report, yes? Get how this works, okay? If I even wanted to go a little bit further and I wanted to say, well, you know, custard has to account for, I don't know, between 30 and 40% of production. I could say, I can add a constraint that says has to be greater than or equal to 30% and less than or equal to 40%. And it would force it into that block. You know, remember, constraints forces, right? Forces it in there and maximizes this as it does so. Okay? As it does. We'll take, I know it's about 7 o'clock. We'll take a break, but I know this is sometimes a difficult concept. So I'll make up a problem you guys can do. Which one do you guys have, what's a problem you guys have access to? You guys want the space range example one handy? Yes? If I put it on Blackboard, you can have it, right? All right, I'll do that. And then we'll add a constraint to that. So I'm going to get that set up. So give me like, come back in like 10 to 15 minutes, and I'll put that out there and we'll work from that, okay? Go to Chapter 3 and click on Galaxy Class Problem. And if you would, open that up. Okay, so you should be at this. You guys find it? All right, so if you go back to the Galaxy Industries, his production mix, I think it was, they made $8 and $5 per dozen for space rays and zappers. And I added jumpers. That's a terrible name, but I'm not a marketing person, as you can tell. And I said $6 for that, and so forth and so on. And if you solve this at this point, okay, if you solve, it should solve to exactly what I have on the screen. Like 320 dozen space rays, 360 dozen zappers, and no jumpers. And I believe the marketing mix constraints that were up there. You guys remember those? Couldn't make more than 700 dozen, I think was one. And I think it was you could not make 350 more space rays and zappers. All right, let's say this. Let's say that we want at least 10% of production in everything, and nothing can account for more than, I don't know, 60%. So everything has to be between 10% and 60%, right? We have to make 10% of every item and no more than 60% of that item. Does that make sense? You guys know what I'm saying? So at this point we're violating that because, you know, we're probably making more, we're not making 10% jumpers. We may be making more than 60% zappers. I'm not sure. I can't do the mental math. But we definitely know we are working off of a summation variable. Okay, so let's create the summation variable. Let's do that first. So I'm going to go to column E, right click, insert, and I'm going to put up here total. Okay. And I'm just going to put a 1 in there to start with. I'm going to need to adjust my formula down here because it doesn't account for that new column I added. So it says sum product B4, D4, B6, D6. We need to change that to sum product B4, E4. God bless you. And B6, E6. And then make sure we copy that down to the other two. All right, so let's first define that total variable. So I'm just going to write over here definition. And I'm going to say space rays plus jumpers plus zappers minus 1 for the total. Copy my formula down. Has to equal, whoops, sometimes when I put in the equal sign, sometimes it thinks I'm going to enter a function in, even though I'm not. So if that's the case, hit the single quote and then put in the equal sign, and it'll treat it as a symbol. Okay. And 0. So what this is saying is space rays plus jumpers plus zappers has to equal the total, right? That's all it's saying. All I want to do, let's not put in those constraints at this point. Let's just see if everyone has this work. Let's take it a step at a time. So go into Solver. And let's see, maximize F6, that looks right. By changing cells B4 through D4, I want to make that B4 through E4. I want to include that summation variable. Okay, F7 through F8 is less than or equal to H7 through H8. That's okay. And now I want to add a constraint that says H9, or it's F9, I'm sorry.
has to be equal to H9. Okay.
So my objective function is F6, my objective cell, B4 to E4. I have to include the summation variable in my decision variables. And here's where I'm defining it. So all I do now, if I solve this, it's going to do nothing differently other than force this cell, which is E4, to be equal to the total of those two things. This constraint created this variable, right? Because I forced it via that constraint to say space race plus jumpers plus zappers equals total. Now, I know some of you smart people are thinking, well, why can't I do it at the sum value? Well, we'll show you in a second. We'll do it with that, okay? So now let's put in the constraint that says all of these have to be greater than, we have to produce at least 10% of every item, okay? Let's put in that constraint. What's that going to look like? Let's do it on the board first. We're going to have to do one for each of these things. But let's say, I want to say space rays have to account for 10% of production. What's that going to look like? X1 has to be what? Greater than or equal to 10% of what? X4. Or another way to write that is X1 minus 0.1 X4 is greater than or equal to 0. Does that make sense? X2 minus 0.1 X4 is greater than or equal to 0. That'll make sure that we make 10% jumpers. And X3 minus 0.1 X4 is greater than or equal to 0. That'll make sure we're making 10% zappers. Okay? So let's add that in.
So I'm going to say for the space rays, this is 1. This is 0.1. Copy that down. Has to be greater than or equal to 0. This one's going to be 1. Oh, I'm sorry, that's negative 0.1, not just 0.1, negative 0.1. Negative 0.1. Copy that down. Has to be greater than or equal to 0. 1. Negative 0.1. Has to be greater than or equal to 0.
Now just by entering this in, I can see which of these is going to become binding. Which of these am I not currently adhering to? This one, for jumpers, right? Negative 68 is not greater than or equal to 0.
Let's tell Excel about all three of these at once. Let's tell Solver about all three of these at once. Add a constraint that says F10 through F12 has to be greater than or equal to H10 through H12. If I solve now,
is forced 10% to be in jumpers. Okay. And change my mix and reduce my profit because it's more binding. And that jumpers is binding. Like this jumpers binding. This means 0. That's solved with equality. What was the second thing? Let's say nothing can account for, it has to be between 10% and 50%. So let's put that in. Okay? Everything has to be between 10%, which I already have, greater than 10%, and less than or equal to 50%. So how's that going to look? What's that going to look like? For each one of them, it's going to be a 1 here, a negative 0.5 here. It has to be what? Less than or equal to 0. Does that make sense?
might as well copy those three lines. just change them. Negative 0.5, negative 0.5, negative 0.5. And instead of being greater than or equal to 0, I'm saying less than or equal to 0, because it has to be less than or equal to 50%.
Now I see what's hurting me here is going to be this one, the zappers.
It's going to become binding because it's violated right now. If I click Solver and I'll tell Solver about those, I'm going to say F13 through F15 has to be less than or equal to H13 through H15. If I solve,
now Galaxy Industries, we have a solution where we're making at least 10% of every item and no more than 50% of total production of any item. Okay? Based on that thing called summation there. Okay? So anytime I'm dealing with that, anytime I'm dealing with percentages of some total, I want to create a summation variable. Things to remember with that. It must be part of your decision variables. It must be something that can change. Because what's forcing it to be the total is this definition of strength. So you have to have a definition of strength. It has to be something that can change. Then you can use it however the problem dictates. All right, I'm going to assign you, we're not done here tonight, but I'm going to assign you from this section a couple homework problems, and then we're going to move on to something. We're not going to get the whole way through tonight, but I want to start it tonight. For homework, I'm in the wrong chapter, that's why it's not making sense. For homework, I'd like you to do number 3 on page 168. That is going to involve the use of summation variables. You don't have to worry about 5. Do number 18 on page 174. That's good for that section. Just do those 2, okay? This is the second section of chapter 3. I'm not sure if we'll cover all of it tonight, but I want to start it tonight. Because next week we'll start chapter 4, and I think next week's week 5, right? So I'll give you your take-home exam next week as well. I'll make it available, right? Week 7 is our midterm. That's when your class midterm is. And your take home is due. All right, so what this section is about is there are some models that require the variables to have special features. And the two features that the variables can take on are they have to be integers. And that one's not hard, that's not a hard concept to deal with. An integer is what? A counting number, right? 1, 0, 1, 2, 3, 4, 5. Those are integers. So a lot of times, models like that make sense when we talk about staffing models. For example, how many people are we going to hire to work this evening? Well, we either hire 3 people or 4 people. We can't hire 3.87 people. It also makes sense when we're dealing with things that are not negligible. If we're saying, how many battleships to manufacture, helicopters, or something where we can't just say, oh, 3.8 is close enough to 4. Something where, it really, really matters, where these things matter, where we have to use the integer constraint. Most of the time we see it in staffing models, when it has to be an integer. We want to avoid integers as much as possible because it doesn't, once we use integers, it doesn't allow us to use sensitivity analysis. We like sensitivity analysis. It gives us more information. More information is always good. So integers not so bad. The one that's a little bit tricky is something called binary models. And we'll talk about those in a second. But sometimes decision variables, we say, have to be binary. What's binary? 0 or 1, okay? A 0 or 1. So not just an integer, but only 2 choices. You either do it or you don't. It's either on or it's off, okay? Binary decision is either go or no, right? So these binary variables allow us to model those kinds of things. Do the project, don't do the project. Buy the plant, don't buy the plant. Invest in this, don't invest in that, right? Make this decision, don't make that decision. So these are used a great deal, and one of my favorite uses of these is called project selection models. Everyone works for a company, and actually in your own personal life, there's more projects than you have resources to get done, right? You may have a backlog of 100 projects. How do you choose which projects to do? Well, project selection models allow us to build a model to quantify what are the best projects to choose, according to these criteria that we put in the constraint. All right, so there are 3 types of integer models: pure integer, mixed integer, and binary. And all those, I don't really care about those definitions, but just know that you can mix these up. You can have a model that has integer, non-integer, and also binary in it. Okay, I want you to know that. So let's talk about binary constraints first. Because integer, we really don't need to discuss. It's so easy to do. I'll show you how to do it. Binary variables and constraints are things where we can model as yes, no, go, no go, good, bad, all those good things. Some examples. We could say X is a new healthcare plan. If it's adopted, it gets turned to a 1. If it's not adopted, it's a 0. X is a new police station being built. 1 if it's built, 0 if it's not. Something of constraint must hold, something if it doesn't. Okay, so let's take a look. Let's give you some examples. All right. I'm going to skip over. We'll come back to this. I'll use the board. Let me make up an example. Let's say at St. Francis, we have 2 potential projects, and we could either build a male dormitory, and let's call that M, or a female dormitory, and that's F, okay? And we either do it or we don't do it. You can't say build 0.87 of the dormitory, or build 2 male dormitories. We're either building a male dormitory or not, building a female dormitory or not. Which means we're going to define these variables as binary. Which means they can only assume the values 1 or 0, on or off. Okay. So let's say Father Gabe, president of the university, tells me that the only way, we have more females than males at St. Francis University, so the only way we can build a male dormitory in this model that you're putting out here is if we build the female dormitory. Okay? Basically what he's saying to me is we can't just do the male dormitory alone and not the female dormitory. It's okay to do neither. It's okay to do both. It's okay to do the female without the male. But it's not okay to do the male without the female. We want to eliminate that combination. Okay? Sometimes I like to draw this out. So if we think about male and female, and they can only assume 0 or 1, then really let's draw a little table. They can both be 0. They can both be 1. We can do one and not the other. And we can do the female without the male. Okay, those are the only 4 combinations, right? Because there are 0s and 1s, there's 2 combinations, 4 combinations. So based on what I said, is this okay to do neither? Is that okay? Father Gabe said, yeah, that's fine. Do neither, that's fine. That's a fine solution. Is it okay to do both? It is, right? Is this okay to do the male without the female? No, he said that's a no-go. So we want to eliminate that possibility. This is okay, where it's all right to do the female without the male. So I want you to look at those 4 combinations. These 3 are okay, and this one is no good. How can we model that mathematically? What is true in these 3 cases that isn't true here? What is true in those 3 cases that isn't true, that's violated in that case that we want to eliminate? Okay. M, well, you said F is greater, but same thing. M is less than or equal to F in every situation, is it not? Here they're equal, here they're equal. M is less than F here. And the one that we want to eliminate violates this constraint, does it? Because M is 1, F is 0. It violates that constraint. So the way we would write this, remember we always want a constant over here, right? So how would we write that? M minus F. That constraint models that situation. Does it not? It adheres to here, here, and here. It's violated here. And remember, as a constraint, if it violates it, it's not an option. Okay. What if Father Gabe says this? You know, we don't want to make either gender upset. So we say, if we do one, we have to do the other. We don't have to do either, but if we do one, we have to do the other. Okay? Either do them together or you don't do them at all. Is this okay? Yes. Is this okay? Yes. How about these 2? No and no. What's true in these 2 that are violated down here? What's true in those 2 that are violated down here? That makes sense. What's true in those 2 that are violated down here? What's that? N equals F. M is equal to F. Or another way to write that is M minus F is equal to 0. That models that situation. Yes? Yes. How about if he tells me this? He says, I don't care about the gender, and I don't care if it's a male dorm or female dorm, but we can't do both. We don't have the resources to do both. It's okay in this current model to do neither. It's okay to do the male alone. It's okay to do the female alone, but we can't bite off both. So this is okay, this is okay, this is okay, but that is a violation. So really we're talking about not comparison, we're talking about combination. How would I model that? How would I model that? A combination. Think about mathematically how we combine things. How would I model that situation? Any ideas? No? Go ahead. Very good. It's plus, right? We want to say the combination m plus f, okay, has to be less than or equal to 1, right? It's okay to do neither. It's okay to do m without f. It's okay to do f without m. But you know what? If we do them both, 1 plus 1 equal to 2. 2 is not less than or equal to 1. Does that make sense? So really, that's it. Those are the three possible things we look at when we deal with binary constraints. Sometimes we force things to be equal. You know, you have to do them together or not. That is this dealio. Sometimes we prioritize things above other things. Prioritizing in math, we use relational operators like less than, right? Less than or equal to meaning, hey, turn it off, turn this one on. This one always has to be greater than or equal to this one, right? That's prioritization. And sometimes we look at combinations. Okay? M plus F is equal to, or less than or equal to 1. If he said, I want to do exactly one and only one of these, how would that change? So he wants to eliminate this situation as well. He wants to do one or the other. How would this change? M plus F then would be what? How would I model that as a constraint? Yeah, equal to 1. We're forcing one to be on, right? I don't care which one it is. We'll let the other constraints map all that out. But M plus F has to, we have to do one, at least one. Well, not at least, exactly one. Okay, so we're going to write that. Exactly. All right, so let's take a look at the slides, and specifically, I think the best way to teach this is to look at a sample problem. So, okay, just going through some examples here. This one says we have 3 plants that we can build, 1, 2, and 3, which is modeled through Y1, Y2, and Y3. If I were saying at least 2 plants must be built, that's a combination problem. Sum of those 3 has to be greater than or equal to 2. If plant 1 is built, plant 2 must not be built. So same thing as a combination. I can't build both of them. Y1 plus Y2 is less than or equal to 1. If plant 1 is built, plant 2 must be built, which is saying plant 2 is greater than or equal to 1. If we build plant 1, we have to build plant 2. We can build plant 2 alone, but we can't build plant 1 without plant 2. It's a prioritization. Y1 is less than Y2, or Y2 is greater than or equal to Y1. It's written that way. 1 but not both plants must be built. Y1 plus Y2 is equal to 1. Forcing 1 to be on. Both or neither, this is setting them equal, saying they have to be done together or not at all. Let's say plant construction cannot exceed 17 million. We know that plant 1 costs 5 million, plant 2 costs 8 million, plant 3 costs 10 million. If those are binary variables, 5y1 plus 8y2 plus 10y3 has to be less than or equal to 17. And why? Think about it. If it's binary, y1 is either going to be one of two values, 0 or 1. If we do it, 1 times 5 is 5 million. We incur the cost. If we don't do it, 0 times 5 is 0. We don't incur the cost. So that's what's very nice about binary. It's either on or it's off. It's either a 1 and it multiplies in, or it adds in, or it's a 0 and it doesn't. Okay? So project selection models are an excellent way to look at this. Okay? Let's skip ahead. I don't like Sunset Beach. I don't know what that's about.
Let's skip ahead. Oh, that's a integer one, and that's easy to do. Let's skip ahead to this one, and I'm going to summarize it for you. Okay, this is probably the best
example of binary variables. And I had a student do, I think he worked for one of the energy companies. They had projects, they have to do, they have money that they use every year to do like refurb of stations and things like that. And he said it was very political battle, like where the money went for every year. You know, they had a meeting and people, squeaky wheel got the oil and all those things. And he took it and he made it a project selection model using like rational, logical kind of factors. And that was the basis. Not that they followed it blindly, but that was the basis for what projects they did that year. Okay? So this is a typical model for binary stuff. Typical elements of such models are budget, space, priority conditions. So this is a municipal example. Salem City Council needs to decide how to allocate funds to 9 projects such that public support is maximized. Data reflect costs, resources, availability, concerns, and priorities the city council has. So here's what they did. Here's the data. We have 9 potential projects. Hire 7 new police officers, modernize police headquarters, buy 2 new police cars, all the way down to buy new computers for the high school. 9 potential projects. Because they're projects, we either do them, we fund them, or we don't fund them. Very much binary situation. We fund them or we don't fund them. We know the cost in thousands. Hire 7 new police officers costs us $400,000. We know the jobs it creates. Okay, 7 jobs here. Modernize police headquarters doesn't create any. Looks like give bonuses to football co-op doesn't create new jobs. So we know the jobs it creates. And they try to gauge utility. What's utility? Utility is like a measure of happiness or satisfaction. By doing a survey of people in Salem, and they said, what do you want us to do? And then they gave points. Like if they got a lot of number 1 priority for this, they gave it 4,176 points. Okay, so this utility point shows the utility or the happiness that our electorate gets on these projects. All right. So we need to choose which of these 9 projects to do. But we have constraints that we have to adhere to. What do you think one constraint is going to be in a project selection model? Why not do all 9? What's going to hold us back? Cost. Sure. We only have X thousands of dollars. Jobs, we may say we need to produce at least this many jobs, right, to make people happy, produce this many jobs. What we're going to do is maximize, we're the Salem City Council, we're hired to make our electorate happy, so we're going to maximize the utility points, right, so that's going to be a function. But there are other things involved here, okay, and I'm not sure it's all in here, but it's in your book, so I'll read them to you. I'll put them on the document camera. It's on page 162 of your book. I'm going to project it up here, though, as well. Okay, so let's get your text out if you want. I'm going to go through this. So let's think about what they want. Okay. $900,000 remains in the budget. You guys told me that's going to be a constraint, right? We can only spend $900K. That's going to end up being a constraint. The council wants to create at least 10 jobs. At least 10 jobs. Sounds like a constraint. All right. Now, here are the ones where some factors come into play. Although crime deterrence is a high priority with the public, the council feels that it must also be fair to other sectors of public service, fire and education. Accordingly, it wishes to fund at most 3 of the police-related projects. I'm just going to write that down in the whole formula. At most 3 police projects. And it's one thing we have to do. The council would like to increase the number of city emergency vehicles, but feels that in the face of other pressing issues, only one of the 2 emergency vehicle projects should be funded at this time. Thus, either the 2 police cars or the fire truck should be purchased. So, fire truck, or what was the other one? 2 police cars. That's constraint. We have some other things going on here. At the top of this page. It says, the council believes that if it decides to restore fund cuts from the sports programs at the school, it should also restore fund cuts from the music program and vice versa. So, restore music and sports together or not at all? If we restore sports, we make the arts people mad. If we restore music, we make the sports people mad. So either together or not at all. And then finally, by union contract, so we have to adhere to that, any additional school funding must go toward restoring previous cuts before any new projects are undertaken. Consequently, both sports funds and music funds must be restored before new computer equipment can be purchased. Restoring sports and music funds, however, does not imply that new computers will be purchased, only that they may. So, computers can only be done, well, it's less than restoring sports, restoring music. Okay? So we can only do computers if we do the other two. So that's what Salem City Council wants to do. They want to maximize utility points. They want to decide which of the 9 projects to do. But we have a boatload of things we have to keep in mind. We have to stay within our budget. We want to create at least, 10 jobs, I think? Create at least 10 jobs. We will at most want to do 3 of the police projects. We want to do either the fire truck or the 2 police cars, but not both, and do at least one of them, exactly one of them, I'm sorry. If we're talking about music and sports, we either have to do them together or not at all. And finally, we can only do new projects, new education projects, if by union contract, if we restore the ones we cut earlier, music and sports. Okay, we have to restore them before we do the other. So what does this model look like? Well, if we were to put this on paper, let's talk about this step by step. Okay, I'm going to go back to this, the kind of the summary of it. What are my decision variables? What are my decision variables in this deal? What are my decision variables? What am I deciding? Yeah, the projects, right? So every project is represented by a variable. X1 through X9 are doing project 1 through 9 respectively. X1 is hiring 7 new police officers. X2 is modernizing police headquarters. These are all going to be defined as binary. meaning they can only be 0 or 1. How much did it say we had to spend? All right, 900,000. So, well, I'm sorry. First, I need to decide my objective function. Maximize, what am I trying to optimize? I'm trying to maximize what? What am I trying to maximize? Utility points, voter satisfaction, right? My constituent satisfaction. If I do project 1, how many points do I get? 4,176. If I don't do project 1, how many points do I get from project 1? So 4,176 times x1, right? If I do it 1 times that, if it's binary, I'm doing it, 1 times that adds it in. Plus 1774 x2, and I'm not going to write these all out because that is very boring to watch that. Plus, I'll go the whole way down to 3003 x9. But be clear, I would have all 9 terms in there, right? Okay, so I'm deciding what projects to do to maximize utility points, voter utility. Subject to. First thing is we have $900,000. Less than or equal to 900,000. 900, it's all in thousands. If we do project 1, how much does that cost us? 400,000. So that would be 400 x1. We do project 2, it costs us, what does it say, 350. So 350 x2. Now go the whole way to plus 140 x9. Now think about all the combinations of those 9 projects we can do. It is literally what? I think 2 to the 9th combination, yes? 2 to the 9th is a big number. I don't know what it is, but it's a big number. My mind can't go through all those combinations, but Excel solver can, right? And it'll adhere to all of the constraints we give it. Okay, this is where computers are fantastic, right? Much better than us. So that would model the cost. I want to create at least 10 jobs. So what would that constraint look like? At least, that's greater than or equal to 10. If we do project 1, how many jobs do we get from that? 7. We do project 2, 0. We do project 3, what does that say, 1? The whole way down to, we do project 9, we get 2. So those are pretty straightforward, those first 2 binary constraints. Let's look at this one. At most, 3 police projects. I want you guys to help me with that. At most, 3 police projects. So we have 4 police projects, 16 combinations. Okay, 16 potential combinations. At most 3. What do you think that would look like as a constraint? At most 3. So we're talking about a combination. So when we're talking about a combination, what do we do? Go ahead. Actually, we don't need a sum. We kind of, I know what you're thinking. You're thinking sum all 4 of those, right? And we do. Yeah, we do have to sum all 4 of those. So we say x1 plus x2 plus x3 plus x4 is all the police projects we do. What about that? What about the sum of all the police projects we do? It has to be what? Less than or equal to 3. I can do none of them. I can do this one and not these 3. I can do this one and not those 3. Think of all the I can do 15 of the 16 combinations, really, right? That does it for me. That would make sure. And if someone said I can do only 2 of, at most 2 of the 4, hey, that's easy. I don't have to think about it. I just change that to 2. But right now it's a 3. Okay? So that's the beauty of this. So done, we have that. This one's saying fire truck or two, we have to do the fire truck or the two, we have to do one and exactly one emergency vehicle project. We can't do neither, we can't do both, we have to do one or the other. That's what the constraint says. You might not say it as clearly as I did, but that's what it's saying. So I either have to do x3 or x5. What would that look like? Very good. The sum of those two, x3 plus x5, has to equal exactly 1. It can't equal 0, because that means I do neither of them. It can't equal 2, because that means I did both of them. I don't care which one I do, but I have to do one or the other, right? So x3 plus x5 is equal to 1. Very good. Okay, this is a little tricky, I know. This one is, we want to keep the art people happy, and we want to keep the sports people happy. So focusing on 7 and 8. We're saying, hey, you either have to do them together or not at all. Okay, you do them both or neither. You can't do one or the other. What would that look like? So they have to be what? They're either both 0 or both 1. So they have to be, what's that? Wait a minute. We're going to get to that in the next one, but if you think about the truth, I mean the table for this. We have sports, which what is it, 7 and 8? Is that one we're looking at? 7 and 8. Okay. 4 combinations. This is okay, this is okay, that's not okay, that's not okay. What's true in those top 2 that's not true in those bottom 2? They're equal. x7 is equal to x8. Another way to write that is what? x7 minus x8 is equal to 0. Now this last one is the hardest one. Because it's actually not 1, it's 2 constraints. The last one said, hey, the only way, I know I'm paraphrasing here, but the only way we can buy new computers is if we've restored cuts to sports programs and restored cuts to school music. So we can never do this computers unless we've done those other 2, right? We can't, by union contract, strongest union in the world, we can't buy new computers unless we've restored things we've cut before. So truthfully, it's like saying this. Okay? If we look at, let's list the sports programs. That's x7. If we look at them alone, that's how I want to look at them. These are the 4 combinations. Is it okay to do neither? Yeah. Is it okay to do both? Yes. Is it okay to restore cuts to sports and not buy new computers? That's okay. So which one is not allowed? This one. We can't buy new computers without doing this. What's true in these 3 that's not true here? Oh, okay. Well, x7 is greater than or equal to x9 in these 3, right? In all these cases, x7 is greater than or equal to x9. Another way to write that is x7 minus x9 is greater than or equal to 0. Think about it. x7 is higher in the priority than x9, right? We have to do that first. So that's why it's greater than x9. It has to dominate. It has to be equal to it or greater than. So that would be one constraint. x7 minus x9 greater than or equal to 0. And think about the nature of constraints. Constraints are adding. They're adding. They're always adding. Okay? So the other one would be x8 minus x9 is greater than or equal to 0. These in concert, okay, these 2 in concert, will make sure x9 doesn't get turned on unless x7 and X8 get turned on. I know that's tough to go through at like 8:05 p.m. On a Tuesday night when most of you have probably been working since 7. But this is what this whole model looks like at the end. Okay? And it's a big one, it's an ugly one. But I think we got it. Okay? We want to maximize all the utility points. Great. Subject to, hey, we have to stay under budget. Fantastic. We have to create at least 10 jobs. Do no more than 3 of the police projects. Buy at least 1 emergency vehicle project. We have to do sports and music together, restoring. And finally, we cannot buy computers, do new school projects without restoring cuts from others. Now, I told you we're not going to go through this because I haven't showed you how to do this yet. I just introduced the concept. I've showed you how to model it up here, but I'm going to show you how to do it with Excel next week, okay? Because we have some time next week. Next week, we will continue this. I'm not even going to give you homework on this. I just want to introduce it. Why don't you read that section if it's still fuzzy, because I know it can be. Read that section in your text. We'll come back to this concept. I have some problems I made up, both integer and binary, that we'll do in class next week. And then we're also going to move into Chapter 4. Chapter 4 is network problems. Okay, network problems, there's a lot of different applications for network problems. So no homework from this section. I just kind of wanted to set this up. You do have homework from the summation variable section. This is, this is week 4. Week 5, next week I'll also give you your take home. We'll go through that, make sure you understand that. Your take home is where you'll actually be using solver to solve things, sensitivity reports to analyze and interpret findings. Okay, so you'll see what that's like. And then 2 weeks from next week will be your actual midterm. Questions. What questions might you have for me this evening? This is one of the quieter classes I've ever taught. Maybe the quieter class. Especially MBA level. MBAs typically, don't take this wrong way, but like to hear themselves talk, you know? You guys don't. All right, well then I will see you next Tuesday. Have a good week.